Hello. This video is about special properties of maps. We can name injective, surjective, and bijective. So here's a definition. Let's take a map between two sets or a function and call it injective or one-to-one if the values coincide, if and only if the inputs are the same. So maps can be drawn, especially if the sets involved, x and a, are finite. So let's have x to consist of two elements and a to consist of three elements, and imagine a map which sends elements like that. And that will be an injective map. So different elements go to different answers, that's what it says. That's the first concept. Then let's define surjective or onto by the property that for anything in the target, so this is an abbreviation of any or anything, there is, and that is the abbreviation for that, an element in the source which is mapped to that element in the target. So a picture of a surjective map will be, say, assuming that we have three elements now in X and two elements in A, and assigning the first two in X to go to the same answer, and then the last go to the remaining answer in A. So that is a picture, the picture for a surjective map. And finally, bijective. Just bijective, no synonymous. So it if it is injective and surjective. So that is both properties together sending different elements to different answers, and any element in the target is an answer. So here's the first fact, that bijective is the same as being an isomorphism. So let me maybe make it a last definition. Is an isomorphism or invertible if so the second name suggests the definition. If there is a reverse map, an inverse map, which goes the other way, and which undoes the original f. So what does it mean? Let's imagine x and a again. So f goes this way, g goes in the opposite direction. So if we follow f with g, we should end up with a map from x to x, and that should be doing nothing map, that should be the identity map. So that is the first condition, f followed by g is doing nothing on x. And the second condition is starting at a, going with the inverse map, and then following with f will bring us back to a, and that should be doing nothing on a, it should be the identity map on a. So that is the first fact, is that is equivalent to being bijective. So let me just start collecting simple facts about these maps. So that is the first map, that bijective, being bijective, is the same as being an isomorphism. So having the inverse. Well, I say the inverse because it is unique. It is going to be unique. You can prove it, and you could actually constructed if you have both these properties, if you have the bijectivity property. So the second factor I want to list is that injective are closed under composition, so composing injective with injective will give us injective, and the same with surjective and the same with bijective. So all of them are closed under the composition. And the last in this list property is that any map can be decomposed into surjective followed by injective, so so-called surjective injective decomposition is always possible, and it is well, effectively unique. So let's start with an arbitrary map now from X to A, call it F. And what can we do? Well, it's just a pure logic. We just look at all the answers, all the elements of the form f of x, and call it the image of f. So that will be all elements in A which have this shape, f of x, for some x. So that is a sub set of A. So we have this natural map which really just tells us how it sits inside, and that is an injective map. An injective map is effectively imagining some set as a subset of A. So that is easy to imagine, that is literally a subset. And then we have a surjective map. We just made it surjective. It's the same f. It just takes x and turns lowercase x and turns it into an element of A, but it becomes an element of the image first, and by the definition this map is surjective. So yeah, these are the shortcut notations for injective. It's either this hook, which is really saying that this is a subset, or you could have this tail on your arrow, and here you have just double arrowhead, indicating that this map is surjective. So any map clearly decomposes like that. There are also, well, you can call them facts, but you can also call them axioms. Assumptions, essential assumptions about sets. They will be facts for finite sets, but if we go beyond finite, they will have to be packaged into the basis. And the first is that any injective map can be split. So what do I mean by splitting? It's a similar situation, but less strict to what we have with inverses. So we have an injective map going this way. We have something going back. And the condition is that if we go with the injective, with the embedding injective map and then go back, we do nothing on X. So that is the condition of a splitting for our map. G composed with F, G following F does nothing. So that is all. Okay, if we have this condition, you could prove that F is always injective. But this axiom is saying that it is if and only if. So what really is involved in, say, producing such a splitting? We have to, using elements inside our sets, we have to, say, find an element X, because we kind of know, we know from this condition where elements from the image of F should be mapped under G. But what about the rest? And that is the problem that is the interesting part in constructing G. So if I start with an element A, and if A is of the form F of something, then that is the value of G on that f of x, because it has to undo f. But if A is not in the image, I'm cramped here, so let me just start again. So if A is not in the image of f, then I have to map it somewhere. And anywhere will do, and that's why I'm fixing some element and then I'm just sending everything to it. So maybe I will call it differently, maybe we'll call it Z, and that will be the formula. So that is effectively saying that we should be able to pick up an element in an empty set. It has to be made clear that it is possible. But yeah, you can argue that this is a moderate assumption. So here's a more serious axiom saying that a surjective map has a splitting. So this time we will have x being surjective, so this is being injective, this is being surjective this time, and we have to go back again, but now the composition of this G and F has to be identity, so that is F following G is identity on A. Again, if we have such, then F is, if we have such splitting G, then F is automatically surjective. But the axiom is saying that it is always possible. So what is involved in, say, constructing such a splitting? It's not going to be unique again. Well, we have to choose an element in X in any what is called the pre-image of A. So any element in A comes from some element in X, but there can be different elements, so this condition is no longer true. There can be different elements going to the same answer. And if we can collect them all, so let's just look at the possible answer F, so say A, and look at all things. This is called the inverse image of the pre-image. All x's in X which are mapped into that fixed A. So we have to choose something in it. We have to choose for each A, we have to choose an element in here. And then we can define G by just saying that G on A is that XA. So that is called the axiom of choice. You have a collection of sets and you choose an element in each of them, and this collection of sets is labeled by elements of some other set. In our case it is A. So this is really equivalent to the axiom of choice. And of course, for finite sets, they are more straightforward. So here is actually a way of singling out finite sets among all other sets by using these concepts of injective, surjective, and bijective. So we could just say that X, define even finiteness in an abstract setting, but say that X is finite. Well, if and only if any injective map from that X to itself is an isomorphism. So yeah, if we have one-to-one map, if we have different elements going to different elements, we have to be surjective, we have to be bijective, we have to have an isomorphism. And it is if and only if the set is finite, because say if X is countable, say integers, we do have maps which place integers in the injective manner in itself, but not not covering everything. So for example, we can just send any integer to twice the integer, and of course we only see even integers as a result, but no two different integers go to the same answer. So that is an injective map, but not not bijective. The same type of calculation is true if we replace in the input, if we replace the our injective map by surjective map. So any surjective map is an ISO also. That is true if and only if our set is finite. So then want to complete it with just a few words about cardinalities of sets, sizes of sets. So let's define the cardinality, or rather, let's just say that two sets have the same cardinality. So that is a notation for the cardinality, whatever it means. Before it was solely denoting the finite number of elements in the set, but yeah, what is a finite number? So we can just talk about sets in the in axiomatic set theory and just say that they have the same number of elements, whatever the number is, even if it is very infinite. So the same cardinality if and only if there is a bijection. So I will just create a shortcut for the bijection, just put this twiddle above the arrow. So if there is an isomorphism of between x and a, making isomorphism between x and itself is a trivial matter because I just can choose doing nothing map, the identity map. It is an isomorphism. So that is defining what is to have the same size, the same cardinality. We can now talk about things being larger and smaller. So I could say that x, the cardinality of, is not larger than the cardinality of a. Just define it if there is an injection, an embedding of x into a. So that is mathematical rephrasing of the philosophical principle that a part, like being a part of a, is not larger than the whole. And here's the fact which is usually proved in axiomatic set theory, that if we have both inequalities, that the size of x is not larger than a, and the other way around, the size of a is not larger than x, then there should be an isomorphism. Then the sizes should be the same. It's kind of looking obvious, but not in this definition, not if we allow sets of arbitrary size. So then it has to be proved, and it is proved. And let me finish with the sort of last partial case of this, an application of this, which is known as a pigeonhole principle. It says the following. So let's assume that the number of elements in X is strictly less than the number of elements in A. So that is assuming that here we have an embedding of X into A, and at the same time X, cardinality of it, is not the same as the cardinality of A. So there are no bijections. There are only possible injections of X into A. So that is the strict inequality. Then we can be sure that there will be no embeddings, no injective maps from A into X. So in another way of saying it, any map from A into X will fail in this injectivity. So any such map called G there will be a pair of elements which will go to the same answer. So these are the pigeons which will have to go into the same hole. If X is a set of holes and A is a set of pigeons, and we have more pigeons and holes, then when pigeons try to occupy these holes, there will be at least one hole where we'll see two pigeons. So again, obvious for finite sets, but has to be proved for arbitrary. So that is it. Next video will be about bijective maps of a set with itself called permutations. So see you then.